Yes, thank you, Yann, for the great talk. Now we will have the second part, which is the fireside chat between Yann and Usama. So please,
Okay.
go ahead.
Thank you very much, Yann. It was actually truly inspirational because it is definitely different than your typical machine learning talk. So I enjoyed that.
Well, I tell you to throw away all the basic pillars of machine learning, so yes.
So I've collected a bunch of questions, some coming from the audience, some coming from our institute and our faculty. And we'll try to go through them in 20 minutes or whatever we can cover. Normally, I would commit to answering every question on social media, but because we got 150 questions, I'm afraid to commit my time or yours to this at this point, but we'll try our best. So I'll start with my first question. It's been a long-standing wisdom in statistical inference and probabilistic reasoning that when the number of parameters of a model gets large enough, you kind of lose your ability to generalize and you start just memorizing data. And we all know that that's no good. That's just too detailed, the bias variance trade-off. But somehow, deep learning seems to have broken through this barrier when we went from regular neural nets to the deep nets. And is there an intuition or understanding today as to why this is working in LLMs with hundreds of billions and now trillions of parameters?
Right. Well, the fact that it is working, that you can train a ridiculously oversized neural net and it will still work reasonably and generalize is dumbfounding, so much that it contradicts every single thing that has been written in every statistical textbook, that you should never have more parameters than you have training samples, right? If you're fitting a polynomial or something like this. But we knew experimentally, even in the late 80s and early 90s, that you could make those neural nets pretty big, and even if you didn't have a huge amount of training data, it would still work pretty well. There was just no theoretical explanation. So the theorists told us, you're wrong, you're stupid, this cannot possibly work, so I'm not going to believe your results. And that's in part what made it very difficult to get neural nets accepted in the late 90s to the 2000s. But it turns out there is a phenomenon that has since been named double descent, which is that if you increase the number of parameters in a model for a constant size training set, your training error, of course, is going to go down, right? To zero, probably. But your test error is first going to go down, go to a minimum, and then go up when you start having parameters, a number of parameters that is commensurate with the number of samples that you have. Okay, so that's when the model starts to be overparameterized. And it goes up. But here's the thing. If you keep going up, if you keep making the model more complex, the test error will go down again. It will go to a maximum and then go down again. It's called the double descent phenomenon nowadays. And it will do this if you regularize the parameters somehow. You don't necessarily need to regularize explicitly because neural nets have some sort of implicit regularization in them. But you see this phenomenon. Even works if you fit a polynomial, right? Fit a 10-degree polynomial with 11 data points. And your fit will be horrible, right? Because the polynomial has to go to every single point and it's going to go wild in between. But if you increase the degree of the polynomial to something like 20 or 30, and you regularize the coefficient, your error goes down again. Your test error goes down again. The fitted polynomial goes through every point, but it's less irregular than with just degree 10. So this existed all along. It's just that people didn't realize it was a thing, or at least people who were not practitioners of neural nets who had realized this was a thing.
But do we have any explanation why this is a thing?
So there's a lot of conjectures. There is some theoretical work. Some people claim it's about the dynamics of gradient descent. There is some sort of implicit self-regularization in neural nets that occurs, whereby the system kind of recruits just the number of virtual parameters that it needs somehow. Some say it's regularization due to stochastic gradient. So stochastic gradient descent, which is noisy, and so perhaps that forces the system to find robust minima in the objective, in the loss, that generalize better. it's not clear. There's a bunch of different things.
Yeah. Definitely one of the mysteries that keep us interested. This question comes from Raman Chandrasekaran, or Chandra, who's one of our senior research scientists in Seattle. How long before LLM and maybe, I don't know, models in general can genuinely start saying, I don't know the answer to this question, as opposed to attempting to guess the right autocomplete anyway, because that's what it's programmed to do?
Yeah, so I think, I don't think current LLMs can really do this at the moment. I think it's probably possible with architecture of the type that I show, because if there are no good minima to the objective that the system is attempting to minimize to produce its output, it's going to say, well, I found this thing, it seems to be minimizing this objective, but not very well, so probably it's not the right answer you were looking for. Or by the shape of the minimum, of this energy minimum, perhaps you could say, like, if it's really a sharp minimum, then that's the one answer that corresponds to the question. If it's kind of a shallow minimum, maybe there are multiple answers that are possible. So you might be able to attribute, to map energy levels of different answers to confidence levels.
Yeah. This is a question from me, I guess. Two aspects of critical importance to, say, GPT or large language models that are not talked about a lot by the companies who do them are data curation. So getting that clean data, that balanced data, that representative data, which, by the way, counter to popular belief, OpenAI spent a lot of its money on curating just that right corpus so that they can do the training reliably. And the second part, which is something we're big believers in at the Institute for Experiential AI. Experiential AI stands for AI with the human in the loop. Having that human intervention through relevance feedback that we know now OpenAI is doing and has been doing, and some of the queries are actually taken over by humans at some point when they make enough errors to come back. But the good thing is they learn from them, and we think that's a great practice. Why do you think the companies don't want to talk about the importance of the data and the importance of the human in the loop?
I don't know if they don't want to talk about it. I mean, it's clearly very expensive to curate data to produce a good LLM. But in my opinion, it's doomed to failure in the long run for two reasons. The first one is the curation, requires going through this, enormous amount of data that you want to train the system on, and any data you eliminate, it's less training data for your model. But the second thing is, even with human feedback, human feedback that rate, different answers or fine-tune the system for certain question and answers, sort of manually curated. If you want those systems ultimately to be the repository of all human knowledge, the dimension of that space of all human knowledge is enormous. And you're not going to do it by paying a few thousand people in Kenya or in India rating answers. You're going to have to do it with millions of volunteers that fine-tune the system for all possible questions that might possibly be asked. And those volunteers will have to be vetted in the way Wikipedia is being done, right? So think of LLMs in the long run as a version of Wikipedia plus your favorite newspapers plus the scientific literature plus everything. But you can talk to it. You don't have to read articles, you can just talk to it. And so if it's supposed to become the repository of all human knowledge, the thing has been trained to do will have to be curated by crowdsourcing the way Wikipedia is to cover all the possible things that may be covered. This is a very strong argument for having open source based models for LLMs. So in my opinion, the future is inevitably going to be that you're going to have a small number of open source based LLMs that are not trained for any particular application. They just are they train on like enormous amounts of data that requires a lot of money. So you're not going to have 25 of them. You're going to have 2 or 3. And then actual applications are going to be built on top of it by fine-tuning those systems for particular vertical applications. That's the future. Sadly, in the industry, there are people who are lobbying governments to actually make the open sourcing of large-scale LLM illegal. What they're worried about is potential misuse of LLMs by bad actors, potential uses. So some people in the US, for example, are worried, if we open source our LLMs, China and North Korea and Iran will put their hands on it, and that's going to be bad. And then some people are worried that the real powerful LLMs are going to be super intelligent and destroy humanity, which I think is preposterous. Even though some of my friends that I respect actually believe this. So I think it would be really, really bad if those lobbying attempts succeed. I'm very much in favor of a future with open-based models. And there's going to be bad actors, but there's going to be countermeasures against them. It's going to be, or powerful, good AI cop against their nefarious AI, essentially.
So let's shift to this trend. And this is, I've merged a question from Jimmy Shanahan from our AI Solutions Hub with questions from Tomo Lasovic and Ken Church at EAI. The trend nowadays seems to be heading towards bigger is better. More compute, more parameters. There's been some studies even suggesting by OpenAI themselves that they're moving at a pace faster than Moore's law, even though now they seem to be normalizing towards it, although Moore's law itself is slowing down. So the real question here is, how long can this go on, and will we asymptote? What do you think? I know that we may not have the final answer here, but it seems crazy. Like all you have to do is wait a few weeks, and you hear about the next big model.
Well, so actually in the last few months, you've seen a decrease in the size. So Llama, for example, the 13 billion version of Llama, in terms of raw performance on standard benchmarks, is actually better than GPT-3, which has 175 billion parameters. And so it's not clear that bigger is better. With the architecture I propose, I think you can get away with smaller systems that perform at least as well. The reason being that when you train in a current autoregressive LLM, you have to train it to not just accumulate knowledge, not just predict the next word, but also solve a lot of problems. So basically, know how to produce a right answer when you specify the question in the prompt. And so everything is wrapped into the weights of that single model. Whereas in the model I propose here, the architecture I propose, the word model is just a word model. The task is specified by the objective function, okay, which may include the prompt. So it may include a representation of the prompt. And so you're separating different things. You're separating the inference procedure that produces the output from the world model, the mental model of the world that the system uses, from the task itself, which is specified by the objective. And you can probably get away with smaller networks for the same performance. But yes, I mean, there were, a few years ago, models by Google that had like 1 trillion parameters. There were basically multiple models that were stuck together with some sort of,
the palm
gating, between them. They've kind of backpedaled on this a little bit. If you want the system to be practical, like to be used by everyone, you can't make them like 1 trillion parameters right now. It'd be just too expensive. So you have to minimize their size. Now you can run things like Llama 7 billion on a Mac. You can run on a laptop. You can't train it on a laptop, but you can run it.
Yes. So clearly you believe you're advocating for a different view what the machine learning and AI community should be doing, as opposed to what they are doing today. And
that's the story of my career.
Yes. and this question is coming from Ken Church, a
former colleague from AT&T.
From AT&T. He is at the Institute for AI in Silicon Valley. Do you believe, well, I guess the question is, how long do you think it will take to pivot the field from where it is to where you would like it to be?
Well, last time I tried, it took 15 years. If not more, actually, depending on how you count. Might have been 20. I don't know. I think I see a phenomenon in the kind of, this is a sociology or science question. When there is something that seems to work, everybody gets excited about it, and there's a fashion trend type phenomenon where every paper written is about this trend. I saw this in computer vision, back in the early to mid 2000s. Everybody was working on boosting. That was the thing. Like you had to work on boosting for computer vision, and then someone in 2006 and 5 came up with a different way of doing vision using dense features like SIFT and stuff like that, using unsupervised learning for the middle layer and then an SVM on top. And all of a sudden, everybody was doing this. Okay, and then starting in 2013, everybody started using convolutional nets. That came from results. So now we are in a phase where everybody is focused on LLMs, and if you don't work on LLMs, nobody wants to talk to you. But it will change.
Yeah. So you think it's 15 years?
No, I think it's more like 5. Like I made that prediction that autoregressive LLMs will probably
5 years. That's true. Yeah, they're doomed.
Yeah, I mean I might be wrong, obviously.
We will hold you to that. I'll come back and revisit in 5 years.
Maybe it's a wishful thinking, self-fulfilling prophecy, perhaps.
A question for something different here from Sam Scarpino, Director of AI and Life Sciences at the Institute for Experiential AI. What are the biggest gaps on the education side for graduates of higher education in AI, and in particular, the new directions AI is taking? What do you think is missing?
So I think what's missing. So it depends which which major you're following. Most computer science curricula in the US are very weak in mathematics. The requirements for mathematics in a typical CS degree, the minimum requirement is very, very small, right? It's one course in discrete math and perhaps linear algebra if you're lucky, maybe probability if you're courageous.
Yep.
But like, what about optimization? Like that would be kind of something that would be very useful. And then there is courses in physics, because the mathematics of inference and variational autoencoder and stuff like that, graphical models, etc. The mathematics of this is from statistical physics. And so if you have the choice between taking a course in, I don't know, mobile app programming or quantum mechanics, take quantum mechanics. I'm not kidding.
This is a question that came from the audience and a few of the people at the Institute. Your thoughts on the current, these recent congressional hearings, where certainly seems like much of the testimony by Sam Altman was understandably self-serving. They need to be allowed to compete and have their way of working protected. At the same time, he's encouraging the rest of the community to be open source. What would you have said to Congress had you been on those hearings?
I was not invited. I was not invited to the White House either before that. So what I would have recommended is that if you want a vibrant ecosystem on top of current AI technology, you need to have sort of open source based models on top of which an industry can be built. And that industry will build vertical applications for particular domains on top of a base model. You don't want to have 25 companies selling 25 different base models and keep them closed source. If you want an industry to be built on top of it, the infrastructure has to be open. Because that's the only way to really sort of know what you're doing, essentially. And to have some control about your future, right? You can't just go like this and pray that
Unix versus Windows.
Right. So if you go back to the history of the internet, there was a similar story where back in 1992, when Bill Clinton and Al Gore started to figure out, like, how do we build the information superhighway? They went to see, the big communication companies like AT&T, and AT&T told them, oh, leave it to us. We'll build the stuff. It's going to be, ATM and ISDN to the home and blah, blah, blah. It'll be wonderful. And you'll have to pay, $5 per hour. And Al Gore said no. He said, we're going to make what was then ARPANET that became the internet, basically available to the public and delocalized and basically open in terms of standard. And no company is going to control it. And that was a really, really good idea. We can thank Al Gore for this. The world can thank Al Gore, not just the US. He did invent the internet. And then a similar story happened several years later when people started to realize that you could use graphic browsers like Mosaic and Netscape and stuff like that, right? When the World Wide Web became popular. So there was a war between Sun Microsystems and Microsoft. Sun Microsystems said, oh, we're going to sell you servers running Solaris, a version of Unix, with our web server infrastructure and Java. And you're going to be able to build like anything you want. Microsoft said, no, it's going to be Windows NT with the IIT web server and the ASP website, server-side protocol framework, whatever. They both lost. Sun Microsystems went bankrupt, was sold for parts to Oracle, and Microsoft essentially exited the market. What won was Linux and Apache, open source. And the reason is because it's such an essential basic infrastructure that it has to be open. It progresses faster if it's open, and it's more reliable, it's more secure. I mean, there's all the advantages, and it's easier for startups to build on top of it. So in the future, we are going to see AI systems as basic infrastructure. All of our interaction 10 years from now with the digital world will be through an intelligent virtual agent that will be with us all the time. It's like every one of us will have a staff of intelligent people working for us. Okay? We shouldn't be threatened by the fact that those things will be smarter than us. Like everybody that is working with me at FAIR is smarter than me. So I don't feel threatened by that. You're not a very good manager if you're threatened by people who are smarter than you. So your purpose actually should be to hire only people who are smarter than you. But anyway, so we're going to have those intelligent systems that are going to be under our control. They're going to help us in our daily lives. And we need those systems to be open because if it's kind of a closed system controlled by some company in California, it's going to be able to control our entire knowledge and data diet. And that's just too dangerous. And it's not necessary. It's necessary for a search engine or a social network because it has to be centralized for various reasons. But for an agent like this, it could run on your local device. It could run on your laptop. You don't have to talk necessarily with big servers in California. You don't want to give all your deepest secrets to that. So it's going to have to be an open platform for that reason. If nothing else, governments around the world are going to insist that this is the case. So that's what I would tell Congress. Make it so that don't ban open source LLMs. They're not going to destroy humanity. Yeah, they're going to be bad actors, but you can have countermeasures. And make it open. It's the only way to make it safe.
We'll make this a quick question with a quick answer, and then I know we have some questions live, so we'll switch to those. In a way, you kind of answered this question when you said LLMs are doomed. But if LLMs were to become perfect, at least in language, would that ever give us insight into how language and natural language understanding works? The language model today is distributed over these billions of parameters. And do you think we'll ever have an understandable LLM, like, for example, we use PCA to understand what regression is doing? Or is that hopeless?
At some point, I think it's going to be relatively hopeless. I mean, we'll probably learn a lot about, how the systems represent data and like how they manipulate it and stuff like that. So this is not opaque, right? We can there's complete visibility on how the systems operate. Now, the question is understanding really how those decisions are being made. So I'm actually not particularly interested in those questions, like, as long as they work properly. The same way I'm not particularly interested in figuring out exactly how the brain works. I'm more interested in figuring out how the brain builds itself so that it works, right? So I'm more interested in learning than in studying the result of learning, if you want. So it's the same for those systems. More interested in how you get them to learn what you want, and how they solve the problem in the end is kind of considerably less interesting in my opinion. But at some point they're going to be, super intelligent, repository of all human knowledge. It's going to be too big for us to kind of comprehend at a deep level.
Fair. And by the way, I failed to acknowledge that question came from Walid Saba, who's one of our senior research scientists at the EAI up in Portland, Maine. The next question I'll use, and then I'll switch over to audience questions, comes from Jean Tunick, the director of AI plus Health at the Institute for Experiential AI. You believe that deep learning can eventually lead to human-like understanding. And you have said that self-supervised learning from unlabeled data can be a powerful tool, although it seems like in human learning, as I was watching your examples, for example, a lot of that data is, in a way, supervised or tied to some kind of reinforcement feedback around what to expect. Is it good? Is it bad?
Yeah.
Et cetera. So where do you draw that line between, can we really truly go towards unsupervised, or there's a huge dependence on supervised and on those labels to get it right? Because the world is, in a way, is telling us indirectly through supervision.
So self-supervised learning, I mean, the reason it's called self-supervised is that deep down it's actually supervised learning. It's just supervised learning where the supervision signal is the input itself, right? Mm-hmm. So in a way, that's kind of, a kind of simple answer to that question. It's still supervised learning in the end, but with particular architectures to handle uncertainty and things, and dimensionality and things like that. Regarding reinforcement learning, there is a point at which you need some form of reinforcement learning, and you need it in two situations, or at least techniques that have been developed in the context of reinforcement learning. The first situation is if the objective function that is optimized by your system does not reflect the ultimate objective function you actually want to optimize. So for example, you're learning to ride a bike. The objective function is time to the next fall or something, or the inverse time to next fall. You want to minimize that, right? But you don't know how to compute this from the internal state of your system. And so you need to train an objective function to approximate this real cost, which in the context of reinforcement learning is called a critic. So that's when you need one of those things. The other situation where you need it is when your world model is not accurate because it's not been trained in all corners of the state space, and you happen to be in a part of the state space that it wasn't trained on. Your world model is going to be bad, and your predictions are going to be bad, your planning is going to be bad. So to prevent this, you need to train your world model using things that are called curiosity or exploration. And that's another concept that comes from reinforcement learning. So don't completely abandon reinforcement learning, but minimize its use.
As we switch over to the live questions, I can't help but ask you this question. It comes from several anonymous people, as well as Ken Church, your former colleague. Did you actually say the revolution will not be supervised?
I did, yeah.
Okay.
But actually, I stole it from Alyosha Air Force from Berkeley. He had a magnificent slide that was a picture of a wall painting in Chile someplace, which was one of those kind of revolutionary thing. And he took that picture and overlaid on it. The revolution will not be supervised. Yes.
Okay.
So I saw that from him. I deserve no credit.
Shall we switch over to a question from the audience?
Yeah. So first question from Glenn Jenkinson is, what 2 questions about AI do you wish you were asked more often?
2 questions.
I don't know. I get asked a lot of questions. I can't imagine a question I've not been asked. That's relevant. I mean, I think the important questions are the ones that I'm asking myself, and I wish other people would sort of frame the problems in the same way. So, big question: how is it that any teenager can learn to drive a car in 20 hours, and we still don't have level 5 autonomous driving? That was the first question. So, second question is, what are we missing? That's the answer I want.
Sure. Next question from Juan Lalinda. Do you think quantum computing will have a significant role in the future of AI?
No. Or at least not anytime soon. By the time this happens, I probably won't be alive anymore, so I'm not taking a big risk. No, I don't think so. I mean, there's precious few situations today where quantum computing could be useful. There's no situation where it actually is useful, because the quantum computers are not big enough at the moment. So it's a huge bet. I think scientifically it's fascinating. Like I'm really fascinated by quantum computing at the conceptual level. I have 1 or 2 papers with Seth Lloyd on connections between neural nets and quantum computing. I think it's a very interesting topic, but I don't think it has any practical value in the short term.
Sure. One last question from Anton de Boer. To what extent do you see ML models being used for problems that we already have pretty good algorithms to solve, such as sorting, shortest path, linear, integer programming, and so on? How would you characterize the boundary, if any?
So there's a lot of problems that we can currently solve that are, NP-complete or NP-hard. And so we can solve them within limits. What we need very often are approximate algorithms, so methods that give us approximate solutions to complex problems that, in theory are NP-hard, NP-complete, whatever. But if you reduce yourself to accepting approximate solutions, might become solvable. So I think there is a lot to be said for ML methods that do something that has become to be known as amortized inference. So amortized inference is this idea that you might have a problem that is formulated as an optimization problem. Every computing problem can be formulated as an optimization problem. And what you might be able to do is solve that problem in certain cases, so you give a solution. And now what you do with this is that you train a neural net of some kind to approximate the solution to that optimization problem from the specification of the problem, from the inputs, right? And so that system will not be able to completely solve the problem in all situations, but for the type of problem that you train it on, it's going to be able to give you an approximate solution really quickly. Amortized inference. There is a tutorial on this that was written and given at a recent conference by one of my colleagues at FAIR called Brandon Amos, AMOS. Very interesting concept.
I will close my questions with one last question, then we'll take a real live one and call it the end. I have to use this. It comes from one of our faculty who wanted to remain anonymous. I don't know why, but given the big excitement around LLMs, and not without a reason, what are some of the research directions that are possible to tackle for non-Google/Facebook type sized institutions that are under studies? Space for foundational research, big open questions, in need of creative solutions. Thus, if you were a young investigator today, like a starting assistant professor, what would you do in this environment?
I mean, that's a problem I have to face when I have, PhD students at NYU. They don't have access to, 16,000 GPUs, right? Unlike people at FAIR. So I think a lot of, like most good ideas still come from academia. So you're not going to beat, Google or Meta or Microsoft on, beating the record on translation or something like that. You don't want to do this in universities. But coming up with new ideas. For example, the problem I mentioned of how do you do hierarchical planning, how you train a system to figure out how to represent the world and action spaces so that you can do hierarchical planning. It's completely unsolved. You can do this with like toy problems. If you have any idea of how you might approach that problem on toy problems, you don't have to have like tons of GPUs for that. You will have an idea that might have a huge impact. If you have like a good architecture that you can show can learn some simple world model from video, it's the same. You don't have to train on like all of YouTube. You can train on artificial environments and stuff like that, and sort of demonstrate that it works. It doesn't have to be like large scale. So this is the kind of stuff you want to do. And then there is a new domain which is building on top of open source based models. So unfortunately, right now, the best base models, LLMs, are the Llama class of models from 7 billion to 65 billion. They're not usable for commercial use. They are distributed with a license that for non-commercial use, so only for research, which you can, of course, use in the university. And there's a lot of work to be done to kind of figure out how to make those things safe, factual, et cetera, and you can work from those base models. You don't have to retrain them from scratch. Yep. So you don't need to have rooms full of GPUs.
We'll try for one last question, maybe two. Go ahead, please, with your question.
Hi. So my question really dwells from the side of, or we'd love to hear your thoughts on impact and control of these large language models or any of these models, the fancy models that you showed with billions of trillions of parameters. So the impact side is, do you really give, or how much thought do you give to the impact that would have on the community or on the people in general based on what that model does? And control is, once that model is out there, how do I make sure that it doesn't do a certain things it's not supposed to do? With regular, the way people used to use internet before those models, it used to be very controlled environment where you could have, in a way, regulate those environments. But now with models, it's getting increasingly difficult and a slow process to have or do not have certain things in those models.
Okay, so there is a long view, a very positive one, which is, imagine that all of us have those assistants with superhuman intelligence. So it's like every one of us has kind of a staff of people working for us, but like super people working for us. This is going to create a new renaissance for humanity, right? It's going to increase humanity's intelligence, however you want to measure it. That has to be intrinsically good. It's been the case, in the past that anytime a new medium was invented or a new way of communication was invented, like the printing press, humanity kind of went to the next step, right? The printing press, led the dissemination of, philosophy, science, secularism, democracy, all that stuff. The U.S. would not exist without, the French philosophers of the 18th century. So, neither would the French Revolution. And so I think, same for the internet, right? That gave people instant access to an enormous wealth of knowledge. Also disinformation, but okay, I mean, we have to have countermeasures for, every technology can be used for good and bad. We need to have countermeasures for the worst aspects. But ultimately, I think we need, widest possible access to those AI systems by everyone. Now, how do we make sure those systems don't lie to us? How do we make sure that the information they give us is not under the control of someone that has nefarious purpose, things like that, which is, I think, a good reason for them to be open, as I stated earlier. But I think it's a bright future for humanity, contrary to some people who tell, young people don't expect to live long, which is nuts. I think it's a very bright future.
I know you've been waiting for the next question, but we are 5 minutes over our time limit, and I know we have to grab a bite and deliver you to the train station on time, according to the hierarchical plan. So with that, please join me in thanking Yann for an amazing session today.
Thank you.